Hello, you guys, and very welcome to today's lesson where we will go through the solution of quite simple but um, like multi-step exercise involving modulus functions, linear functions, and yeah, a bit more. So, without further ado, I will share my screen to go first through the exercise. So we will be basically we're given a graph showing the function 2x minus 3k, the modulus of this, right? So it's given to us, and k is set to a positive constant. We want now to use this graph to sketch k minus modulus of 2x minus 3k, where we'll have to find the coordinates of the turning point, but also any intersection points with the axis of x and y, so the x and the y intercepts. And yeah, that's the question here. Let's see if I can just then move to the PowerPoint explaining the steps that I took to explain that. All right, so we'll be sketching the graph, and I just wanted to give a bit of a background because if you are an A-leveler contemplating very good marks, then you have to be prepared to a situation where this graph is not fully given to you. Okay, it's not plotted to you, or not at all, right? It would be up to you to do the job. So the question is, could we just plot the modulus of 2x minus 3k in some way, some sort of form? This will require us to go back to the definition. So I'd be asking you, what is the modulus of x? What's the modulus of 5 and what's the modulus of minus 5? Well, the answer is 5 and 5, meaning you always return a positive answer. So really, when you're generalizing, modulus of x is very easy if x is positive. You'd just be taking the same number. But if it's negative, you'd have to take that number and get rid of the minus. So mathematically, it would be through multiplying by minus 1. That would just neutralize the minus. Or, as we usually put it, modulus of x is just minus x if x is negative. Okay? And they both agree if x is equal to 0. That's why the 0 is possibly to include in both expressions. So of course, in this case, if we're having the modulus of 2x minus 3k, there'll be two cases. Either it will be actually the same value, it will be 2x minus 3k, or it will be minus the argument, okay? And what will decide what this is, like which it is, will be the value of x with regards to k, right? So on the domain where 2x is so larger than 3k, the difference would be positive, and so this will be the answer for the modulus. And on the range where x is too little, the answer will be then minus 2x plus 3k because the argument will simply be negative, okay? Now, if we were to plot y equals 2x minus 3k, right? Sorry, this one, I mean. Or y equals minus 2x plus 3k, we'd get just two straight lines, right? But because of the limitations, half of the straight lines will be cut off in the following way. This is the curve of the straight line with a negative gradient, roughly minus 2. I tried here with the squares, but it's going down. The y-intercept is 3k, but that would only be valid for x bigger than 3k over 2, which is the 0 point of the modulus function. Okay, so we'll have to get rid of this that part, like the part where x is too big. On the other hand, plotting 2x minus 3k will give us an ascending straight line, but as this will only be valid for x larger than the 0, right, we'll also get rid of that part of the line, right? This mid, like this half straight line will basically be cut off. I'm also taking the opportunity to actually put a minus 3k here as the y-intercept because it will be useful in the future, in the very near future. So because, like I said, of the ranges, this will be the y with the modulus we're contemplating, okay? So that's kind of the background as to why that function looks the way it looks. So if I then go back and just plot it, right, with the y-intercept and the x-intercept, and I want now to move to our real curve, so k minus, yeah, exactly. So moving from this one that was given to us, I want then to construct the f of x. So I'd have to do it. Then the question would be back to you, like how could we actually use this one to move to f, right? So obviously we're going from the modulus to minus modulus, which means that we have a first transformation mapping y onto minus y. If we would just, disregard the k value here, yes? So how do we move from modulus to minus modulus? It will basically, be thinking that with the same x value, you get the same answer for both functions. Only in the top functions you will get the positive y. So let's put some x here. This is the y corresponding here in the red curve, but the same y will be then returned by the lower curve here, only it will take the negative value, right? So let's say for 0, for instance, we'd have 3k in this case. If we put a minus, it will just get mirrored about the x-axis. So our graph will be mirrored about the x-axis, and that will give us the minus modulus, which is then the first transformation we have to undergo in the way of building the f graph. Then we'll have to add the k, and that's literally what we will do mathematically as well. We will be incrementing the minus 2x minus 3k modulus by a k value, which is furthermore set positive. So definitely, how do we move from here to here? We will add a k. And in graphical terms, as we've seen that already in the GCSEs, this means we'd be translating the curve k units upwards, and this is our new graph, right? That's the graph of the f function. It will cross definitely the x-axis here in 2 points. It will cross the y-axis, although it's difficult to say where, as for now. And it will also have a turning point or a maximum point, which completely confirms the exercise's goal. And that's it. So without further ado, we just move to decoding all of this. So I'll go back to that curve with the minus modulus. I'll add a k and just remind that we'd be moving up. I will keep the 3k over 2, which is the 0 of the minus modulus function. And because it's a minus modulus function, this value would correspond to the maximum of it. It's a 0 y value corresponding to the x being 3k over 2, right? I'm going to keep as well the y-intercept of minus 3k because all of this will be a great background to continue. Now, finding, well, the y-intercept to start with. So the y-intercept could just be taken as minus 3k and then moved k units upwards. So minus 3k plus k, we're expecting minus 2k here, right? Or, of course, because the y value is given here to minus 3k, um, yeah, then adding k, sorry. Yes, that's that I already said. This I already said. Or the other way to actually calculate this is to, considering it's a y-intercept, the x value has to be zeroed, okay, in the blue graph. So I just put x to 0, and that will give me k minus the modulus of minus 3k. Because it's a negative value, it will return 3k, and k minus 3k is minus 2k. Not surprisingly, the y-intercept is at 0 x-axis minus 2k y-axis, and we're happy with that. The maximum, like commented earlier, and we could just kind of elaborate on that, the maximum will be reached for this function also when the red function reaches its maximum, given that everything is just translated upwards. So that will be when the modulus function hits 0. And the modulus function hits 0 when x is equal to 3k over 2. And if I plug in 3k over 2, it will zero me this value, not very surprisingly, and I will get y returned to k, right? Just simply the k here that I translated from 0 and then k units. So the maximum point will be located at 3k over 2 and then k in the y direction. And finally, right, make this react. So the x-intercepts. And the x-intercepts are more interesting because they will make us solve an equation that's a bit more fun, like just slightly more complex. And of course, if it's an x-intercept, it's the zeros of the function. They are literally reached when the function is affected the zero value, and then we'll have to solve this for x. So this evolves to modulus equals k being positive. This equation does have solutions, okay? So since it's a modulus, we said about it that either it returns the argument itself, so 2x minus 3k modulus will just be replaced by 2k minus 3k, and we'll solve this for k, so it will give us then, just by rearranging that, x is equal to 2k. Or we'll also have the modulus returning the minus value, like the opposite value. So it'll be minus 2x plus 3k equalized to k. By rearranging this, we'll get x equals to k. And of course, it's always good to check this against the graph. We have two x-intercepts. One x-intercept would be for k, the other x-intercept would be for 2k, and the y is 0. Looks good. The only thing that's missing here that absolutely will get you the last points and also prevent you from making mistakes, kind of arriving to false solutions, is to actually not forget the conditions on the modulus function. So this, which is the first one here, would only be valid if actually 2x minus 3k is positive, meaning for x superior or equal to 3k over 2, this condition, giving you a solution greater than 3k over 2, is the only one possible. Like you would return a value of, I don't know, 0. Here, you would be happy because you found a value of 0. That would be then a false root because it doesn't abide by the very condition making you able to change this modulus by the argument. Does this make sense? Because it's really key. And at university, we'll be waiting for you with some banana, on the floor to make you slip and fall on it really hard if you don't remember these, right? So we want you to make you check all the time your solution, 2k, very nice, but then against the condition that makes it possible to get, which is greater than 3k over 2. 3k over 2 is 1.5k, so this is safe, right? And then again, in this case, the second one would only be valid for x less than 3k over 2, because that's when the modulus is exchangeable by the opposite argument of minus 2k, minus 2x plus 3k, right? But this passes the filter because k is actually less than 3k over 2. But I'm telling you, like I've been doing countless you know, like exam marking. That's what it's called at uni. And that kind of non-checking is just fatal. So we do, wrap this up being happy and on, you know, on destination, like just arrived where we were headed by identifying the two x-intercepts to 0k and sorry, that should be k0 and 2k0 because they're x-intercepts. Sorry, I was busy doing a lot of animations with this PowerPoint that I just wanted to finish real quick, and still I was able to make some um, mistakes I didn't have the time to correct. So 2k 0, are we there? Yes, ta-da! Now it's done. Um, I hope you enjoyed the exercise as much as I did. It was absolutely delightful going through this, and I hope we'll catch up soon. Thank you very much.